This is a video for AQA Discrete Mathematics, Graphs and Networks, section 3.3, where we're looking at minimum cuts on a network flow graph. Well, firstly I need to define for you what we mean by a cut when we're talking about flows in a network. So a cut is literally a line which cuts across the graph, dividing the nodes into two separate sets. One which contains the source S and the other set of nodes containing the sink T. So here we have what we call the source set, which would be SA, and then a cut, and then the sink set would be BCD and T. Now, how many nodes there are in each of the sets isn't the point. The first set, the source set, must contain S and as many of the others, and the second set must contain the sink T and the rest, and obviously all of the nodes are in one set or the other. The value of the cut is then the total of the capacities which are going from the source set to the sink set. So if you look at that particular cut there, the capacities that are going from S to, or the source set to the sink set, include the 8, which is going from S to D. So we've got S to D, size 8, and we've also got the 12, which is going A to B. But if we look at the other arrows, they're coming from the sink set into the source set. So DA is going in, if you like, the wrong direction, and CA is also coming from the sink set into the source set. So it only includes those which are going from source into sink. So the 8 and the 12 giving us there a total of 20, or a value of 20. Well, let's look at another example of a cut, this time coming down this direction. So we've got there the source set, which remember must contain S. It also contains A, B and D. And the cut with then the sink set, which contains C and T. If we look at those which are going from the source set to the sink set, then we have got 4 going from D to C, and 15 going from B to T. The others are going the wrong direction again. C to A, C to B are both coming from the sink set into the source set. So here we've got a value of 19. Sometimes the cuts that we're looking at can be quite convoluted. So for example, let's look at this one, which comes round like this, and then down like there. So what have we got there in our source set? You can see that including with the source we've got S, A and C. Then the cut puts the others B, D and T in the second set. So B, D and T. Now in these you have to be particularly careful to make sure that you get the correct thing. So for example, the 4 going from D to C, that's actually going from the sink set into the source set. So the ones that we're then looking at across the cut, we've got from S to D, that's going from the source set into the sink set. So we've got S to D is in the right direction, 8. We can also look then at those that are coming from C. We've got from C to T, and that has a value of 7. From C to B, that has a value of 8. And then the other one that we need to consider is from A to B, which has a value of 12. So actually quite a large total value there of 35. We might ask, what's the purpose of all these cuts that we've been looking at? Well, there is a theorem which is known as the maximum flow minimum cut theorem, which states the following. It says that the maximum flow through a network equals the value of the minimum cut. So far, if you think back to what we've done here, we've found cuts of value of 35, 19 and 20. So far we know that the maximum flow cannot be greater than 19. So the flow through a network cannot exceed the value of any cut. It also means that if we can find a flow equal to the value of a cut, so if we happen to have a cut of 19 as we have at the moment, if we find a flow of equal to 19, that must be a maximum. So the max flow min cut theorem says that the maximum flow through a network is equal to the value of the minimum cut. Well, here's a possible flow that we had in an earlier video. Remember the capacities here have been circled. The flows are in the blue numbers that are on there. And we had there a flow through our network equal to 12. And we might say, well, okay, is that a maximum flow or not? Is it possible to increase it? Well, I think you'll see that it's very easy to increase this by adding some more along from S to A to B to T. So we can actually increase that up to 10 coming into here, and then 12 coming into there. So adding an extra 4 and 14. So we've now got a flow equal to 16. And the question would be, well, can we go any further than that? And you'd probably look around and say, well, it doesn't look like we can. So, well, is it therefore our greatest? Can we prove it? And if we can find a cut which has got a capacity or a value equal to 16, then that must mean that our flow that we found of 16 is a maximum. And it's actually quite a straightforward one. It comes down here, and that cut, which goes with S, A and D, cut with B, C and T, then we've got the arc going from D to C, which has got a capacity of 4, and an arc going from A to B, which has got a capacity of 12, and we can see therefore the value of that cut is equal to 16. So that would prove then that the flow is maximum. Well, that concludes this video on the max flow min cut theorem. In the next video we'll be looking at how you deal with what are called multiple sources and multiple sinks. In other words, where we've got more than one source and more than one sink. Several reservoirs supplying 2 or 3 towns. So all of the water from the 3 reservoirs goes into 2 towns, for example.